a significant number of people who've been working very hard on trying to show that you can get verifiable quantum advantage, and I think Andru is one of the people who has been working the hardest on it. And, so he has a lot to tell us about it.
Thank you, Umesh, and yeah, thanks for having me. So this is going to be a more theoretical talk compared to the previous ones, but hopefully you'll still find it interesting. So as Umesh kind of hinted, it's about trying to figure out who's basically going to win this horse race of verifiable quantum advantage. So let me first say what I mean by verifiable quantum advantage. So I would argue that like all of us in this room, unless you happen to be here by accident, are looking for a problem or a computational task that satisfies the following properties. So it should be efficiently solvable by a quantum computer and hard to solve classically. From a complexity theoretic perspective, this would mean like polynomial time solvable on a quantum computer and ideally exponential time solvable on a classical computer. It should be efficient to verify the results of this problem classically. So it should only take like polynomial time again, and in practice it should be efficient so that we can like scale up the problem and keep being able to verify it. And the third thing is that we want it to be near-term implementable in the sense of either being able to implement it with a noisy quantum device with maybe a lot of qubits but like limitations in connectivity and depth, or with one of the early fault-tolerant devices that are, say, like within the 100 to 200 logical qubit range, where I would say that we don't yet have very good candidates for what to run on those devices. Obviously, we know when we have larger devices with like thousands of logical qubits, we can do like Shor's algorithm, quantum simulation, and so on. So those are typically types of problems that would satisfy like conditions 1 and 2. And things like sampling tasks, so like random circuit sampling, the famous quantum supremacy result of Google that we heard a bit about from John's talk. So that would satisfy 1 and 3, but it's not really efficiently verifiable at scale. And of course, we might also want it to be useful, but that's maybe a concern for a later time for us theorists, at least. I'm obviously kidding. We do want things that are useful, but it would, of course, be very interesting if we can find something that satisfies at least the first 3 conditions in a very convincing manner. And in this talk, I'll propose like one candidate that we've been thinking about, which is to start from this problem introduced by Aronson in 2009 called Forrelation. And I'll kind of give a few arguments for why we might want to look at this problem. But first, let me just quickly explain what it is. Excuse me. So the problem is the following. Imagine that you're given access to 2 functions, f and g. So these are Boolean functions, which take in n bits and output 1 bit. And really what you're trying to determine is whether one of these functions is correlated to the Fourier transform of the other function. In other words, if you were to like list out the truth table of the function f and the truth table of the Fourier transform of g, you want to know like how correlated these 2 things are with each other. And that's encapsulated in this expression that you see here, phi of f and g, which one typically refers to as the correlator of these 2 functions. And we pick the functions in such a way that we're promised that they're either very strongly correlated with each other, so this quantity is large in absolute value, or they're not. So this quantity is like close to 0 in absolute value. And this might look fairly abstract if you've not seen this before, but actually from a quantum circuit perspective, it's like a very simpler, it's a much simpler picture. You simply put all of your qubits in a superposition, then you evaluate a circuit that essentially implements f, like the functionality for f. You then Hadamard again, you do the same thing for g, you Hadamard and you measure, and the correlator will be the amplitude of the all 0 outcome of this circuit. So you basically want to see like how often am I seeing all 0 in the output if I run this circuit. And just to be clear here, like what are UF and UG? So these functions f and g will have like some sort of circuit implementation, and what these UF and UG should be is the circuits that will implement these functions in the phase. So, UF acting on a state X is going to give you like -1 to the f of x ket x, and similar with UG. Okay, so let me give you some facts about Forrelation, like why we think it's an interesting problem and potentially something that could give us verifiable quantum advantage. So first, we know that classically this seems to be a very hard problem. So if you only have black box access to these functions, like you can only make queries to them, but you don't actually have the descriptions of them, then you can actually prove that the number of queries you would need classically to compute this Forrelator or estimated is exponential. It's roughly 2 to the n over 2. In fact, even if I do give you like classical circuits that implement these functions f and g, in general, we don't know how to solve this problem efficiently. And again, the best classical algorithms that we have for it require, again, something like 2 to the n over 2 runtime. And of course, I should highlight that from the picture I showed you on the earlier slide, clearly this problem can be solved efficiently with a quantum computer. What's interesting also is that even computing the sign of this Forrelator, like let's say the Forrelator itself is just a real number, and your promise that it's either, like strongly positive or strongly negative, you want to distinguish these two cases, even this seems to be hard classically. So there was a very recent paper showing again that like if you have just black box access to these functions, you need exponentially many queries to determine what the sign of the Forrelator is. And I mentioned this because that's actually what we'll be working with later on. Okay, from a complexity theory perspective, it's also interesting because there's a variant of Forrelation which you can show is not in the polynomial hierarchy, and there's also another variant of it which we know is BQP complete, so it kind of like fully captures the power of like polynomial time quantum computation. But the question is, like, if we actually want to run this problem on a quantum computer, the first question is, like, what are we going to use for the functions f and g? Like, how do we instantiate the oracles? And I argue that, like, one natural choice we could make is low-degree polynomials. So, so like f and g here, you should just think of like as multivariate polynomials of low degree, like say degree 3, degree 4, something like that. Because even in this case, like say even when the two functions f and g are like degree 3 polynomials, it still seems to be hard to say compute the sign of the Forrelator. At least like in this case, we don't have very good like formal evidence for this. Like we can't really prove query complexity lower bounds in this setting. But at least, again, like we don't know of any efficient algorithm that could do this better than this like 2 to the n over 2 runtime algorithm that we have. And I should also say that like, a degree 3 polynomial requires just order n cubed coefficients to specify. So it has like a very compact, so to speak, representation. And therefore, the circuits that would implement these like UF and UG unitaries would have on the order of like n cubed Toffoli gates, and the depth of the circuit would be like n squared. So this means that, if it actually happens that the best classical algorithms for solving this problem really scale like 2 to the n over 2, then even taking little n to be like on the order of 200 or something would already give you quantum advantage. And 200 would mean like roughly, I guess, 8 million Toffoli gates. And what will the depth be? Well, thousands, I guess. Yep. Yeah, that's a great question. That's what I'm going to talk about next. Yeah, so obviously, whatever functions you pick for f and g should be ones for which you can actually ensure that the Forrelator is like large. So it's either strongly positive or strongly negative, because if it's just like very close to 0, then we can't, like even quantumly, you might not be able to learn what the sign is. Okay, so this is exactly Fernie's question, which is like, how do we pick these functions? And let's say we're like even stricter than that and say like we want the Forrelator to just be +1 or -1. So it turns out that there is a family of functions that will achieve this, which are called bend functions, and which have been studied in cryptography for a while. So these are functions for which, so we say that a function f is bent if basically its Fourier spectrum is completely flat. Like each value of the Fourier transform is just plus or minus 1 over square root 2 to the n. So it's like completely flat, and you just basically change what the signs are. So you can show that if you have a function f which is bent, and you pick the g function to roughly correspond to like the signs of the Fourier transform of the f function, then you will get that the correlator between f and g, so if g is like, exactly the signs of the Fourier transform of f, then the correlator will be 1. And if it's like minus the signs, then the correlator will be minus 1. So this is like an easy way in which we can choose these functions to achieve this property. And then the natural question you might ask afterwards is it easy to come up with these bend functions? And the answer is again yes. So there are several constructions. One of them is called the Majorana-Macfarlane construction, which basically says I can split the input to my function into 2 halves. So x1 and x2 are like n over 2 bits each. And the function is just the inner product of the 2 halves, modulo 2. And then you can add any function, any other function that only acts on the second half of the input there. So h here is like any Boolean function, and you can show that this function will indeed be bent, like it will exactly satisfy the definition from above.
So the question is,
yeah.
The usual quadratics won't work for you with this bent, like quadratic.
Right, very good. So the reason we don't want to use quadratics is because then the circuit is Clifford, and then you can just simulate it classically. So degree 3 is like the lowest for which we don't know how to classically simulate this efficiently. Yeah.
Yeah. Does this construction work for other partitions which are not equal, not n by 2, n by 2?
Oh, I'm not exactly sure. So it's possible. So the inner product function itself is a bent function. So if you're asking,
I'm pretty sure the answer is no. But
okay.
Like, doesn't every bent function have to take in an even number of inputs or something?
Yeah, maybe you're right. So you mean like partitions of different sizes?
But yeah.
Yeah, then probably not.
But certainly this construction. Like,
sure.
The inner product is 2 halves.
Right. Okay. Okay, so let's say we use bend functions. And let's make another simplification that, at least like at a circuit level, it might make things a bit easier, which is, let's consider what's called self-correlation. So we're looking at what the correlator is of the function f with itself, which means like g is equal to f. And these are called self-dual bend functions, and these also exist. So there are examples that you can construct of self-dual bend functions. So now the circuit looks like this, like you just have the f function twice. But actually, there's a simplification we can make here, which is by noticing that, what is this circuit doing? So on the left side, we have a bunch of plus states. And here, what we're interested in is like the all 0 output, which if we absorb the Hadamards into the measurement is like the all plus outcome. So the correlator is this quantity. It's like basically the expectation of this thing. And if I put in these UF unitaries, which are like these phase operations, as I mentioned before, into the plus states, then you get this state ket f, which is just an equal superposition and encoding the function f in the phases. And the correlator then is just the expectation of the Hadamard observable with respect to this state. And this is nice because it means I can just prepare many copies of this f state and then just measure the Hadamard observable on the state to kind of see what the correlator is, which is quite nice. Okay, so in general, this expectation is easier to compute than something like a transition amplitude, which would be like if f and g were different and you had something like this instead. Okay, so now let me tell you about the approach we have for trying to make this classically hard and easy to verify. I've maybe just told you so far like how you could plausibly get an instance of correlation that's classically hard using these like degree 3 polynomials and bend functions. But the next question is then like, okay, but how do we verify this? Like we need to add some extra structure in there. So if you were here for the, I guess like quantum cluster in the summer, I gave a previous talk about this where we had this approach of like obfuscating these polynomials using an affine transformation. But then like Noah Shuddy right after my talk pointed out that actually this can be solved efficiently classically. So that was broken. And Noah's not here, so I guess we're fine with this new approach that I'm going to tell you about. But obviously, like I'm giving this talk also because I'm hoping that the community will think about the classical hardness of this, and of course, it would be great if we learn one way or the other whether the problem is easy or hard. Okay, so our previous approach was to try to obfuscate the function. And then what we realized was, what if we obfuscate the observable instead? So what if instead of trying to compute the expectation of Hadamard, we compute the expectation of some other observable, which is either a +1 stabilizer of this F state or a minus stabilizer. I don't know if that terminology is like strictly speaking kosher, but what I mean is like the F state will be either a +1 eigenstate of the thing that you're trying to estimate or a -1 eigenstate. Okay, so let's kind of study this a little bit. So let's denote as G sub F the stabilizer group for this like ket F state that we're considering. And what we'll actually be looking at is a subgroup of the group of like all stabilizer operators. I'll show you on the next slide what the stabilizer group will be. But just a few comments to make about the stabilizer group here. So because this ket F state is like a degree 3 phase state, so it requires like magic states to prepare, it turns out that these stabilizers will all be Clifford unitaries. So this group is a subgroup of the Clifford group. It's not abelian. It's also in general not going to be like a normalizer of the Clifford group or something like that. So it's just going to be like some weird non-abelian group consisting of Cliffords.
Is there an easy way to see why it's Clifford?
Yeah, so it's because the unitary that prepares F lives in the third level of the Clifford hierarchy.
Okay.
And then when you commute, you're going to get a Clifford. Yeah. So if we had like degree 4 or higher, then these unitaries would not be Clifford. They would be like, more general unitaries. So at a high level, what we're going to try to do is to sample a random element from the group or the subgroup in this case. So let's say V is the random element we sampled. And then we're going to add potentially a minus sign to this operator and ask the quantum computer to estimate the expectation with respect to this W that could potentially have the minus sign. And so the hardness that we should rely on is that if I give you this W, you can't really tell if it's a stabilizer, like if it's a +1 stabilizer or a -1 stabilizer for the state. And so I'm going to comment a bit about like the classical hardness of this task. But first, let me just like give you like the entire what the protocol would actually look like. So step 1 will be, we'll pick an F, which is some degree 3 polynomial self-dual bend function. So something for which the expectation of Hadamard is already +1. And then what is this subgroup that we're going to choose? So the way we construct the subgroup of stabilizers of F is by looking at the symmetries that this F state satisfies. So on the one hand, we know that Hadamard is a stabilizer by construction because it's a self-dual bend function. And we also know that like this state we got by applying this like UF unitary, which is a unitary that's like diagonal in the computational basis onto a bunch of plus states. Now the plus states have the poly X's as stabilizers. So if you conjugate the poly X's by the circuit that prepares this F state, then you will get stabilizers for this F state. and these will be our generators. So you pick, randomly operations like that, and then you combine them, and this will generate some subgroup S sub f of stabilizers of this state. And this might not necessarily be the entire group. So for instance, we found examples of functions f where you also have like poly y's as stabilizers, which you could never have arrived at from something like this. So in general, this is just going to be like some subgroup of the set of, the stabilizer group of this f state. And again, like this is a subgroup of the Clifford group. And it turns out to be quite large, also because it's a non-abelian group. So for instance, when we had like a function f on 6 bits, the size of this group was something like this, like 660 million. Okay, so you generate, like we have the generators for that subgroup. We use them to pick a random element in the subgroup, call that element v, and then multiply it by a random phase. So b here is just a random bit, and we add a random phase. And now we take this w, which is a Clifford circuit, and we compile it into some canonical Clifford representation. So for instance, like the Aronson-Gottesman representation. And then we just send this like compiled Clifford to the quantum computer, and we ask it to estimate this expectation. Note that like W might not always be unobservable, so you might want to add in this constraint as well. If not, you can just ask it to estimate this. It's just that the circuit will become slightly more complicated if W is not unobservable. Okay, and here's one interesting fact. So if I were to just send you W in terms of like its implementation from the generators, like the circuit that I would get by just putting all the generators together, then obviously you can just figure out what it is and see whether it's like a +1 stabilizer or a -1 stabilizer. So the key step is compiling this W into a canonical form for the Cliffords. And this canonical form is essentially unique. Like there is a way to take any two circuits that are Cliffords, which implement the same unitary, and compile them into one Clifford that implements that unitary. So this is, in the crypto jargon called like perfect or statistical obfuscation. And this is effectively hiding how we constructed this W. Like I'm just giving you, like the unique representation in this canonical form of W. And hopefully I've hidden how it was implemented in terms of the generators of that subgroup. Okay, so now the million-dollar question is, how hard is it to classically compute this value? Like, is this problem, so I should say that, the person who picked W and B will know whether the sign should be +1 or -1. And the question is like, now the quantum computer or the person claiming to have a quantum computer, when they receive the description of the function f and the description of the circuit for implementing W, can they tell whether this value will be +1 or -1? That's what we need to determine. So we have like verifiability, we have an efficient quantum algorithm to implement this. The question is whether we have classical hardness for this. How much time do I have? 5 minutes, okay, perfect. Okay, so, I can't really tell you any like lower bounds on the hardness of this because we haven't found any. So I'm just gonna tell you some upper bounds that seem like kind of, closely tied to the problem itself. So first, like, notice that, first of all, this problem is just like a more general instance of the self-forrelation problem itself. Because this W is not Hadamard, like it could just be something else. So it's like more general than this self-forrelation problem. But it turns out that there is a reduction to forrelation. So if you can solve like regular forrelation, you can also solve this problem. And the reason this is the case is because every Clifford admits what's called a Bruhat decomposition, where you can just express the Clifford as a circuit comprised of like CZ gates, C naughts, phase gates, Hadamards, and then again like phase CX, CZ. And I should say that this is only symmetrical in form, but the CZs here, like the circuit of CZs here, is not necessarily the same as this one. Okay, it's just that the form of the circuit will look like this. And let's get rid of the phase gates because this W will have only real entries in our case anyway. So if we look now at like this expectation that we're looking at, and we decompose W in this way, we can just absorb the CZ and CX gates into F and get these like new phase states G and H. And now we're again computing essentially a type of forrelation for these functions G and H. It's just that like the Hadamard now doesn't necessarily act on all the qubits. It might act just like on some subset of them that came from this Bruja decomposition. But this basically shows that if you can solve like almost regular forrelation for G and H, then you can also solve this other problem. Another interesting connection is to group membership. So I told you that this W was picked from this like subgroup of the Clifford group, the subgroup associated to the state F. So you can view this as, like you can think of the following problem. Suppose I give you a list of generators for this group S sub F, and I also give you a description of W. And what I'm asking is W part of that subgroup or not? Because if it's a +1 stabilizer, it is, and otherwise it's not going to be part of it. So how hard is this problem? So clearly it's an NP. Like if the answer is yes, then I can just give you a decomposition of W in terms of generators. And what's interesting is that we can show that if you can solve factoring and discrete log, then you can also solve this problem. So it's quite interesting that we also have an upper bound on our problem that's basically just factoring and discrete log, which a quantum computer can solve efficiently. And that's, I think, kind of interesting. So why is this the case? Let me just maybe like very briefly go over it. So behold the symplectic group, which is what happens when you quotient the Clifford group by the Paulis. So there is a homomorphism from the Clifford group to the symplectic group, and you can consider this constructive, this group membership problem for the symplectic group instead of the Clifford group that we were considering. In other words, you take this homomorphism, you apply it to like all of the generators that you were given for S sub F. You also apply it to W, and you ask, can you find a decomposition in terms of these like phis of the generators for phi of W, which is like asking this like group membership question for a subgroup of the symplectic group instead of the Clifford group. And if you do find it, then it means that W itself is going to be of the form, whatever product you found of the generators, and then times some Pauli, which a priori you will not know because the symplectic group is like modding out the Paulis. So like we lose the information about the Pauli. But it turns out that, if this is the case, then you know that the expectation of this W is just, the expectation of, P times this thing. But this part we know should give us +1 because it's the generators. And so it's just the expectation with respect to this Pauli, which we don't know. And this can be computed efficiently whenever F is degree 3. It's kind of for a similar reason to the question that William asked, which is that, again, like the circuit that prepares this F state is in the third level of the Clifford hierarchy. So if you commute the Pauli past it, you will get a Clifford. And then what you'll get is just the expectation of a Clifford with respect to like the all zero state. And this you can efficiently compute classically. So this means that if you can solve the group membership problem for the symplectic group, then you can solve the problem that we're considering. And this is just a subgroup of like a general matrix group. And we know like there's this famous result by Babai et al. From 2009 saying that you can actually solve this problem if you have an oracle for factoring and discrete log. And if you're wondering like how big are the numbers that you would have to factor with this, they're going to be, in this case, like on the order of 2 to the 2n. For factoring, this is not great if n is like on the order of hundreds, but for discrete log, it's fine. Like for discrete log, classical algorithms usually scale is like exponential in n. Okay. So I basically, sorry, was there a question? Okay, I'm just going to wrap up here. So obviously what would be interesting is if we can show, a matching lower bound. Like, I think it would be kind of wild if this problem also turned out to be at least as hard, so basically equivalent to factoring and discrete log. That would, of course, be very strange and interesting. But even if we can't show that, like any other plausible classical lower bound that we can give would be very nice. And of course, the question then is how big of an instance would you need to actually demonstrate quantum advantage? And I think one approach that would be really nice to explore is to use ideas from this recent paper by Ilango and Lombardi, where they showed that if you assume the existence of one-way functions and indistinguishability obfuscation, then you can instantiate the oracle in Simon's problem. And maybe one could do something similar here. And there are also more general questions about the hardness of Forrelation for low-degree polynomials. But yeah, that's basically it. So thank you.
There's a quick burning question. Maybe.
I'll be quick. Just to make sure I understood correctly, the stabilizer, the Clifford stabilizer group you defined, it's basically a product of X and CZs and also Hadamard's.
Yes.
Okay. Yeah. Thanks.
Yeah.
Hi, very nice talk.
Thanks.
I think you said that Forrelation is still hard for degree 3, but then you had to do this other thing where you obfuscate these stabilizers. And why do you need to do that if it's hard for degree 3? Or
Because we don't know how to verify it in general. It's hard, but if I just pick arbitrary degree 3 functions or something like that, then I won't even know what the correlator is supposed to be. I have to pick them in a way where I know what the answer is, but where the quantum computer doesn't know.
right, for the ones you're picking, which are these self-dual bend functions,
Yes.
then it's not hard anymore, and that's what you need to do obfuscation.
That's right. Yes. Yes.
Okay, thanks a lot, Andru.
Thank you.
We now have a 20-minute coffee break, and then we'll be back for the panel discussion.